Hey, welcome. So you write a line of code, you hit enter, and poof, something happens on the screen. But have you ever really thought about what's going on in between? Well, today we're taking that exact journey, from an idea in your head all the way down to an instruction a machine can actually understand. Let's dive in.
All right, so here's our game plan. First up, we're going to tackle the main problem. How in the world do you even talk to a machine? Then we'll look at the brilliant solution that makes all of this possible. After that, we're going to peek under the hood and see the mechanics of how your code turns into real action. And finally, we'll talk about the most critical piece of the puzzle, the human mind behind the code.
Okay, let's kick things off with the biggest hurdle right away. You've got us, humans, who think in ideas and feelings and abstract concepts, and on the other side, you've got this cold, logical machine. So how do we bridge that massive gap?
It's a question every single one of us asks at some point, right? It's so easy to just think of programming as typing some magic words. But what's really happening is a translation. It's about learning to give instructions that are so ridiculously precise, so literal, that there is zero room for misunderstanding.
Okay, first things first, you gotta get this in your head. Computers are not smart. They don't get nuance. They don't understand your intention. What they are is incredibly, blindingly fast and perfectly obedient. Think of them as the most powerful, but also the most literal-minded assistant you could ever imagine.
So what is this super literal language that they speak? Well, it's called binary. At its core, a computer only understands one thing: electricity. Is a circuit on? That's a 1. Is it off? That's a 0. Every single thing your computer does, from showing this on your screen to calculating a massive equation, boils down to a gigantic, mind-boggling sequence of these ones and zeros.
Okay, hold on. If computers only get these massive, endless streams of ones and zeros, how do we tell them what to do without losing our minds? Well, that brings us to the absolutely brilliant solution that makes modern technology possible: the language bridge.
Before we get into the languages themselves, let's just demystify what a program even is. It's not magic. A program is just a recipe. That's it. It's a list of super specific instructions for the computer to follow, one after the other. Nothing more, nothing less. And this shows the translation process perfectly. In our head, the idea is simple: add 2 numbers. But to a computer, you have to spell it all out. You have to say, hey, computer, make a little box, call it A, and put the number 5 in it. Then make another box, call it B, put 3 in it. And only then can you say, now add what's in those 2 boxes and show me the answer. Every single step. And that right there is why programming languages are our best friends. They are that crucial middleman. We write our instructions in a language that's pretty readable for us humans, like Python. Then a special program, our translator, takes what we wrote and converts it into the pure binary machine code that the computer can finally understand. So we've been talking about this translator, but right now it just sounds like some kind of magic black box, right? How does it actually work? Let's get into the nitty-gritty, the mechanics of how your code actually comes to life.
Turns out these translators really come in 2 main flavors. A compiler is like a book translator. It takes your entire program, reads the whole thing from start to finish, translates all of it at once, and then hands you a completely separate, ready-to-run file. Languages like C++ do this. An interpreter, on the other hand, is like a live translator at a press conference. It reads one line of your code, executes it, then moves on to the next one. Python and JavaScript work this way, which is why you can see things happening line by line. So let's follow the whole journey. The moment you hit run, the system first does a quick grammar check on your code, what we call syntax. If that's all good, it gets converted into that binary machine code. Then, the computer's brain, the CPU, starts chewing through those binary instructions one by one. While it's working, it uses RAM, like a messy desk or a notepad, to keep track of all its data. And finally, whatever the result of all that work is, it appears on your screen. You know, this gives us a really helpful way to think about the computer's mind. The CPU, that's the brain. It does all the heavy lifting, all the thinking. The RAM is its short-term memory. It's a total scratch pad. The second you turn the power off, poof, it forgets everything. And then you have the hard disk. That's the long-term memory, where all your programs and files live safely. All right, we've spent a lot of time on the machine side of things. But here's the deal. Programming is a partnership. So let's flip the script and talk about the other, and honestly, the most important half of that partnership: the human, and what it takes to think like a programmer. Look, you're gonna get errors. I get errors. Every single programmer on Earth gets errors. It's just part of the game. A syntax error is basically just a typo. You forgot a semicolon. A runtime error is when you tell the computer to do something impossible, like divide by 0. And then there's the sneakiest one, a logical error. The program runs fine, no crashes, but it gives you the wrong answer because the idea in your head was flawed to begin with.
And this brings us to probably the single biggest mental shift you have to make. You have to stop thinking of errors as your enemy. They aren't a sign that you failed. Every single error message is the computer trying its absolute best to tell you, hey, right here, on this line, this is where your instruction got confusing. They are your guide. They're your teachers.
Let's just blow up the biggest myth in programming right now. Forget the movie scenes of someone typing like a maniac. That is not what programming is. Real programming, like 90% of it, is about slowing down, leaning back in your chair, and just thinking. Thinking really, really clearly about the problem you're trying to solve.
And that really gets to the heart of it all. Learning the words of a programming language, the syntax, that's the easy part. Seriously, anyone can memorize that stuff. But being a good programmer, that's about being a problem solver. The code is just the tool you use to build the solution. So there you have it. We've gone from a simple thought in your brain, through a language translator, and into a series